Well, good morning, everybody. Welcome back. To the ones came yesterday, welcome to the ones arrived today. This is the second day of the event, Mathematical Aspects of Topological Insulators. And for the people that just arrived, this is held at the Institute of Mathematical Science of the Americas, that lives here in the University of Miami. And as the director was yesterday saying, it's a place where one can apply for 1 week's events. And the institute, if they accept it, they will finance it. This institute is partially funded by the Simons Foundation, partially by the University of Miami. So it would be good to think about more workshops similar or like this one in the future. So we have now Professor Regnault, did I say it correct?
Yep.
That I'm very happy and glad that he accepted the invitation. He's doing some world tour.
Saving the planet.
Saving, no, well, I'm saving the planet, but
one trip at a time.
So, Professor Regnault is a CNRS, professor in the Ecole Normale Supérieure, also in Princeton. We're very happy to have you here to tell us about Moiré fractional phases of matter.
Thank you.
So you have an hour.
I will try to make it shorter, so we have a long coffee break.
Good.
Thank you for the invitation. It's a real pleasure to be here. It's a very nice place. We walked by this morning. The campus is just amazing. So today I will talk about some work we have done on twisted TMDs, the Princeton University version 9, and how we can have bases similar to what we have in fractional tomorrow emerging there. The work was done, I mean, it will show you different results and put on the diverging lots of people, but let me acknowledge like a few main contributors, and these are the students, of course, from Princeton, Javin Yu and Yves Kwan, who are both postdoc. Javin, I think, will move soon to Florida, if I'm correct. Yves will look for a postdoc, so looking for good candidates is one of them. Also, Glenn Wagner from Zurich, University of Zurich, will be also on the market next year. So, and also this guy, Valentin Crepper from the Flatiron. So you have lots of good people if you want to hire this. People. Okay, so it wasn't clear what would be the audience. So it will be maybe some historical part about the quantum Hall effect first. And why? I mean, talk a lot about quantum Hall effect. It's basically, the first example of a topological phase. So I'm not sure. It's very, as a brief reminder, topological phase can be described by symmetry breaking, and that is a monoclonal parameter. And we assume that there is at least one physical quantity that we can relate to a topological invariant. Being a math, more math-like conference, I don't think I need to introduce the concept of the topological invariant. The system is gapped in the bulk, and the edge could be either gap or gapless. But most of the time, if you think about the case of the quantum Hall effect of the minimal bar, you have a gapless mode, which is chiral, so that you cannot strictly realize in one dimension, but you live at the edge of a two-dimensional system. And the way we realize quantum Hall effect is by having electron gas confined in 2 dimensions under a very strong electric field and at low temperature. So we have the usual picture of the Landau level, and when you measure the longitudinal resistance Rxx or the whole resistance Rxy, you see plateau in the longitudinal resistance, the transverse resistance, and zeros in the longitudinal can attribute to the presence of this topological phase. So when you have an integer filling of this Landau level, you have a quantization of the whole conductance, which is universal quantity and with a metrological precision up to 10 to the minus 9, and that is related to the first Chern number of the band. That will also explain why this quantity is so robust. So the story doesn't end with the integer quantum Hall effect, and there's a question: what's going on if you look at, for example, the lowest Landau level and the fitting which is lower than 1 for this band. And I mean, naively speaking, you would say, well, I have one Landau level, let's say I have 2 electrons in 6 orbitals, any of these configurations have the same kinetic energy. So you need another ingredient to leave the degeneracy there. And of course, what we forget in the future is, well, you do have interactions. And that's how you will have phases which are also kept in the bucket, will present like plateaus in the whole resistance and zeros in the shear resistance. And really emerge from the combination of the non-trivial topology of the band and the strong interaction. The most celebrated example is the fraction that you observed at the thin factor 1/3. And just for this picture here, just have a look at the value of the field. You're something around 30 Tesla. So that's the point that we will address soon. It's an example of a topological order basis. So you have fractionalization of the charges, and not only free to move in the system, and they also not only have fractional charges, they do have fractional statistics or even non-abelian statistics. Which is still, after so many years, a challenge to show experimentally. So remember the exchange statistics, you have two indistinguishable particles that you exchange. What you have learned is the wave function should be identical to the phase. If the phase is 0, here you get bosons. If the phase is pi, you have fermions. And the simple fact that you have these two different possible phases will allow you to explain lots of physical phenomena, just the fact, for example, you have the Pauli principle, and that's an insulator. But you know that the story doesn't end here. If you're in strictly in 2 dimensions, you can have something richer than these two statistics. That's the abelian ions if the phase is a fraction of pi. But of course, there is no restriction to only phases. You can have something richer like matrices, and that's what would rise to the abelian ions. The most famous example being Majorana fermions, but you do have generalization like power fermions. So experimentally, there was some recent progress in showing direct evidence of fractional statistics. 2 types of experiments, either using interferometry or noise measurements. So this is an example of an collider that was developed in Paris, where they have been able to show effect of this abelian ions. A bit of marketing, why people are so interested in these non-abelian ions, well, there's all the question of creating quantum computing directly based on non-abelian ions, rather than using a logical qubit that you create from many physical qubits to create error code correction. But I'd say from a physical point of view, as a physics point of view, just showing that you have in nature an abelian ion is good enough just motivation to work on the topic. Oops. No. I'm French. Hey, I'm French. Okay, I know. And really, it's important to stress that all this very nice physics, even though you can have lots of very powerful mathematical framework around it, is still built on experiments. And there is, we should celebrate the progress that people have made in creating devices, like even in gallium arsenide. If you look at the history of the fractional automotive effect, the first observation of the fraction 1/3, until the last, this is one of the most recent experiments from James Book, when we had a massive amount of fractions observed, people have been able to really improve their samples. If you look at the mobility of the sample, basically you have more than 2 or 3 orders of magnitude improvements. So that's the story of the fractional automotive effect. And let me tell you what it is a fractional insulator and why people are so interested in these systems. There is 2 drawbacks of the quantum Hall physics or the fractional quantum physics. The fact that you need low temperature. All these experiments I've shown you, like maybe the last one was around 10 millikelvin, and you need a very high magnetic field. So, and we know from more than maybe 35 years now, that you can have a Chern band without any external magnetic field. So there is a question, can you get the same phenomena than you have in gallium arsenide electromagnetic field, but without any external magnetic field? For the integer quantum Hall effect, that was observed for the first time in 2013, and there is like continuous improvements in getting better materials, better samples, and so on to try to reach the same kind of accuracy when it comes to the quantization of the Hall resistance. The quantization of the Hall resistance is very important in metrology because that's when you define the unit of resistance. And many labs would like to have, like a portable device that they can use as, a quantum resistance standard. And that's basically like what many groups are trying to do around the world. So having a system where you don't need this very low temperature, this very high magnetic field, and still provide this standard. So that's for the integer case. And of course, the natural question is, can we have the same thing for the fractional quantum Hall effect, namely the same type of phases, but without any external magnetic field, and maybe at a higher temperature? Say, what I need is what? The Landau level is an ideal Chern band perfectly flat with a pretty large gap, which is given by the cyclotron energy, if you forget about the spin for a moment.
Quick question before you go to the fractional
Yeah.
case. This integer case, this quantum anomalous Hall effect, how precise is the quantization there?
So I think they are able to do something around 10 to the minus 5. But people in metrology, they are really trying to, there is a question of domain size, depending on where they put their contact and so on. So there's some averaging effect that prevent them for the time being to reach the same kind of accuracy that we have in the more traditional gallium arsenide system. So, can we realize the fractional quantum Hall effect without the magnetic field? Well, you could say it's pretty simple. Let's take any model that gives us a Chern band. This is a very simple one. It's a tie binding model where you have two orbitals per unit cell. So once again, spinless fermions. So you have two bands. You can cook up this model to have a non-zero Chern number, let's say Chern 1 for the top or the bottom band. And one way to see it is, for example, you put your system on a cylinder, and if you look at the energy spectrum as a function of the momentum, you have, of course, the dot state in black, and the blue and the red states in the gap corresponding to the two chiral nodes located at each end of your cylinder. So let's imagine I take one of these model and I just include strong interaction between my electrons. Of course, not too strong to not reduce band mixing. And that's what people did in the early 2010, even 2011, like trying to build time models where you could have a fractional chain series, so the analog of fractional Hall effect, but without any external magnetic field. There is a large literature about FCIs. In a nutshell, it looks a lot like the fractional Hall effect, but there are some, of course, and the Landau basically like Landau levels physical strong interaction, but there are some details that, for example, I will discuss when we will deal with the actual experimental system. From maybe a more mathematical perspective, there is like a recent trend over the last 3 or 4 years to try to make a more rigorous mathematical mapping from an F fractional chain insulators to the fractional quantum Hall effect. It has different names. I will show you some results when it comes to the concept of ideal or taxable Chern.
Can I ask a question?
Yeah.
So, how essential is it to have a Chern to get a fractional Chern insulator? Is it necessary, or is that just the easiest way you can think of? Is there a theorem that says you have to have a Chern?
A theorem, no, not in mathematical sense. Now, all the example that I know, all this story is, of course, tightly related to numerics. So if you forget about the mathematical structure, which require a Chern band and even a specific type of Chern band, all the rest is basically based on numerics. And if you look at, if you make your system trivial, but you still have interaction, usually you destroy your fractional Chern interface. So I would say it's mandatory the same, unless you have some very specific interaction, because of course you could say, I have a flat band, I don't have any kinetic energy. So everything is encoded in the projected interaction. So if I find some, really weird interaction that mimic exactly the same calculated set, I should get also FCI bit. But if you take any reasonable lattice model and that you can turn from topological to trivial, then you will, as soon as you go into the trivial phase, you will kill your fractional Chern insulators.
So, but at this point, it's sort of a rule of thumb, right? I mean, so maybe there could be some. You could imagine that it would be necessary to have some pathological long-range interactions if you don't have a Chern band. Could there be possibly some?
Yeah, you could basically you would say the Chern band will give you what? It gives you the algebraic decay of the vanilla state, which gives you the frustration that you need to rewrite the state. So maybe you can trade off the short-range interaction, the unprecedented one, with a long-range interaction that would give the same physics.
Can I maybe have a follow-up? I could imagine a band which was like kind of minus cosine t. So it looks like this, and I can take t, so it gets smaller and smaller. Maybe there's a way that you can distribute like all the Berry curvature, like compensating in the middle and the edge. And if you partially fill it, then you're kind of feeling locally as if you may have a Chern number, even though like globally over the whole Beryllium zone, you don't. I mean, it seems like you could kind of pick up that kind of Berry phase type of physics there. I mean, it seems like it may be possible if you have fractional filling.
No, I don't say that. That's why I'm really careful about saying, is it mandatory? I have no proof. The only thing I could rely on is...
Right, no, I'm just saying that there might be a way that you could construct a model numerically to investigate the question.
So even though, I was part of the people that started this trend in 2011, I think it's really important to stress that it didn't come out of nothing. There was, of course, you could say, fractional component effect in the lattice as a long story, back to Cohen-Reed that look at the interplay between the lattice and the physics. Fractional component effect in spin system. So that's basically Kennedy and Laughlin back in the early 80s. In the 2000s, there were also people looking at how to realize fractional component effect in cold atoms. Fractional component effect doesn't depend, doesn't bother dealing with fermions, the bosons. You can replace your fermions with bosons. It doesn't get the same physics. So one way to have FQH in cold atoms is basically to try to do like the Hofstadter model. So take a square lattice and the magnetic field. You can try to engineer that in cold atoms, and with the interaction between the bosons, you should give rise to fractional quantum physics. That was studied by Fezzi and collaborators, and also Gnarr and Nigel in 2000s. And of course, the big motivation at that time was, well, topological insulators. And Charles King, of course, was here. So the idea of this very beautiful non-interacting physics can be generalized to the interacting case. So that was basically the motivation of this FCI work. Okay, so that was for the theory side, based on toy models. What about the experiments? The idea is, well, can we go to zero field? So there were several steps to the process. There is some work on graphene over HDN substrate done by the group of Andreas Young at UCSB. They still require an external field. Also from the group of Jacobi on twisted wire graphene. These were, just to be technical, what they probe is the gap. The gap is the bulk is gap or not. They don't look at transport measurement, which is from, if you listen to people in microscopic physics, they say that's the real signature of fractional physics, that you have a zero of the shape resistance and a quantization, the plateau for the whole resistance. But it's still going in the right direction. And last year we had two groups, one group in the University of Washington, Seattle, and a group of people at Cornell, that's in twisted MOT2. So at zero field, they have observed bulk gap in the bulk at fractional field, like minus 230 here. To some extent, this physics is actually, there's a question whether or not this is already like fractional chain insulators or more related to the object of physics. Basically because you're in a regime where the mass clamp will be comparable to the typical distance of your Moiré lattice. But also, this is a fast-moving field, and if we have the
But those
first...
experiments were done in zero field.
Which one?
The one on the upper right? Is it
Yeah.
that? And how is it related to Hofstede's butterfly?
But not this one. I'm talking about these two.
Oh, those
So
two,
this
okay.
one is clearly
Okay.
strictly zero field. Apart, from, because you have a series phenomena, so you need like a small field to choose one direction or the other, which is exactly what you have here. So in August, we had two papers, one from the people in Seattle and another group in Shanghai, where they did the actual transport measurements on this twisted MOT2, so the externality field, where they have observed quantization of the whole resistance at the thin fraction 2/3, so which is like the minus one that I've shown, the minus signs because you're dealing with the balance band, and there is some symmetry between 1/3 and 2/3. That's another fraction where they have observed the quantization of the whole resistance, and you see more or less zero of the resistance. We are not yet at the same level of accuracy as what you have for gallium arsenide by far. It's, if you listen to Xiaodong Xu, who's the head of the group at Seattle, he says basically that his samples are really dirty. Mobility is like over 10,000. So even worse than what people had in 82 when they observed for the first time the fractional Hall effect. But still, despite that, it's there. And it's there at temperature, so it's 8 Kelvin for the integer case. For the fractional one, I think they still observe the quantization up to 2 Kelvin. So it's a major improvement compared to what you had in gallium arsenide. So at the end of the day, what is the difference between an FCI and a fractional Hall effect? Well, it comes to the different options that you have in an FCI system. Because here the bands are not perfectly flat. So you have the dispersion curve, the block band, you have an non-uniform quantum geometry, and the physics can thus be richer. You can have competition, of course, between a fractional chain insulators and a fermi liquid. If you have dispersive band, as Greg was pointing out, if your interaction are too strong, basically you have a Fermi sea. If the interaction are stronger, then you might be in a regime eventually of an FCI. But even among the gap phases, you have different types of such a phases that can also be appearing in the system, like a charge density wave. There is also a cool point compared to a lambda level. You can find system with a higher Chern number. Then the physics is slightly different from the Bayer fractional Hall effect. This system, even though we make the equivalence between the Chern band and the lowest band level, they will appear, they don't break naturally the time-reversal symmetry. So the interaction will actually break the time-reversal symmetry, giving rise to a ferromatism. And this ferromatism does not appear all the time. So maybe a better way to phrase the system is not really fractional chain insulators, but more like fractional topological insulators. And why this is pretty exciting, because you have lots of proposals that say, well, if you have a robust fractional topological insulators, and you couple it with some superconductivity, which is not a problem anymore because you don't have any externality field. Well, there are some technical detail, experimental detail about copying these TMDs with superconductor, but even the experimenters are moving toward the ability to really have a deposit to to have these ferromagnetic contacts in TNDs. But basically, that's a way to engineer non-adding anions. And that's why, I mean, people are so excited about this system.
So, quick question about
Yeah.
this system. So what is the magnetic order in that when you're in this fractional Chern insulator phase?
You get a ferromagnet for most of the time. So the your system I will show you that you spontaneously polarize your system. You have the valley and that's the locking for it, and you just polarize your system, but not at full fractions. Yep.
What happens if then you start as a non-zero 2K daily index?
I will address that question in the last part of my talk. But basically, there are all these experimental systems. You can, and that's related to the question of Greg. You can see them as two bands with opposite Chern number, so with opposite magnetic field. But they have a U1 conservation on top of the time response symmetry. So it's that's why experimentally they observe the quantum spin-Hall effect not only at by filling one band but also by filling two and so on. So there is no Z2, but it's more or less just U1 symmetry. Okay, so how do we get Chern bands in this MOT2 system? Let me roll back to somehow a more famous example of Moiré materials, basically twisted graphene. So you take two layers of graphene on top of each other and you rotate one compared to the other. You have two different regions. So whereas graphene you have two atoms per unit cell, call it 1A and 1B. So in some region of your twisted graphene, you have A atoms on top of the A atom, and another region where you have A atoms on top of the B atom. Basically, how do we deal with that system? The unit cell that you will consider for small integrals is very large, so there is no way you can deal with so many atoms, or it would be really painful. So what you do is to simplify your graphene to just the Dirac codes. You have one per valley, K and K prime. You can think about your system in momentum space. So that's the Moiré, the Boolean zone red for one layer, the other one very blue. And when you do the Moiré, the Boolean zone of the Moiré is way smaller. And what you have to do is to fold the Dirac code, which is at one K point, from its original Boolean zone of graphene to the one of the Moiré. And when you introduce a coupling to two layers, you will get down by symmetry. And you know that for some specific angles, the first one will be around 1 degree. What you get is two very flat bands around the zero edges of the gap. So they are not only they are flat, but they also are non-trivial. So I've realized that there is mathematical, I think in the title of the conference. So I will briefly show you some results about TEG, which are more mathematical to justify the need. There is a very neat way to understand these two bands, which is called the Carroll limit. So the idea is the following: when you are in the region AA, you have a certain type of interlayer hopping between the two graphene layers, and there is another one in the AB region. So in a very model that is McDonald, that's one of the parameters that you need to capture the physics there. Basically, the ratio between the AA and the AB hopping amplitudes omega 0 to omega 1. And the Carroll limit is just to take the AA hopping amplitude to 0. If you do that, your system will have an additional Carroll symmetry. And so at zero energy, you will have the two perfect flat bands, and they are eigenstate of the Carroll symmetry operator, and actually each of them has a different Chern number. So you can see, you can imagine, you can picture these two flat bands act like two Chern bands with opposite Chern number plus and minus 1. And they have some very nice properties which are related to the story I was mentioning about ideal Chern bands. So ideal chain band is a concept to really try to put the mapping between a fractional chain series and fractional topological effect on a more mathematical ground. And you have different conditions in the literature to qualify a band, a chain band as an ideal chain band. One of them is a trace condition. So basically, the trace of the quantum metric should be equal to the very curvature up to a factor given by the Chern number. It's called trace condition. Another one, which is maybe more mathematical, is the concept of vortex stability. The concept of vortex stability is something very simple. If you look at the wave function, the one-body wave function of the lowest Landau level in the symmetric gauge, they look like this. So a polynomial in the complex coordinate of your electron, x plus psi y. And you see there is something funny because you can get, so m is basically tied to the angular momentum of your state. And you can get any state at momentum m by multiplying by z to the n. When you have Bloch band, I mean, multiplying by some coordinate doesn't mean anything. So all the idea of vortex stability is to try to put that kind of concept into Bloch band. Actually, what we have shown is that you can relate all this concept to the idea of mapping rigorously the Chern band to a generalized lowest Landau level. So by generalized, I mean where your electrons they live on a space with a given metric and with a non-uniformity field.
Is the vortexability related to the flatness of the band in any way, or that's an independent?
It's independent. It's based only on the wave function, not something in the flatness. But as usual, in that kind of story, you can, the flatness will be important when you when you compare the interaction energy to the kinetic energy. But all the information about getting the same algebra, like the multi-translation algebra, in the case of a Chern band, everything is encoded in the wave function of the band. And basically, the reason why the twisted biography is interesting is you can make it's a continuous parameter. There is no lattice anymore, and you can show you can basically relate the wave function of the Moiré bands to the one of this generalized Landau level, and it's basically putting some homomorphic structure on the Bloch band of on the wave function for your Chern band, and that's the TDG is one example where it works.
Nicolas?
Yep.
So I'm trying to understand the first constraint that you have there, or the opposite, I guess. If there's chiral symmetry and you have two bands, are they not gapped out?
No, they are. It's like.
So what protects them to be exactly at zero?
It's the chiral symmetry, like you have for the SSH. If you have a chiral symmetry, your edge modes are located exactly at zero.
Not because they have one. Not because I have one. And if I have one state per edge, then there's no way to split it away from zero energy. But if I had two, I can split them away. Related.
But they have different. They're
Maybe we can
yeah.
discuss it later.
I'm not sure.
You say they are living in different chiral sectors.
Exactly. Yeah. The eigenstates with
So
different
they
chiral
cannot
numbers.
they cannot couple each other.
And of course, you will start coupling them as soon as you move away from this, because you break the chiral symmetry if you take some A coupling. But as long as you preserve the chiral symmetry, because the eigenstates, each of them are eigenstate of the chiral symmetry with different eigenvalue, then you're fine.
Yeah, precisely because of that. If they have different chiral charge, say, and they are both degenerate, I can combine them to open a gap. If they have the same chiral charge, then I wouldn't be able to split it away.
Okay, maybe we can talk about that and if you think about it. So another more mathematical result that, why this flat band in TPG is so robust. Well, actually, it shares some analogy with the lowest Landau level, not in the RTC system, but in graphene. So in graphene, the Landau level at zero energy has some very specific structure. Basically, it has some additional index that protects it, or the RTR index. And actually, that was shown a few years ago. Basically, what people did was to look at graphene magnetic field and put some disorder in the coupling between the atom of graphene, and they take some corrected disorder with the correlation length beta. And as long as the correlation length is a bit larger than the typical distance between the atom of graphene, you can show the following results. Namely, if you look at the density of states of your electron, graphene, and electromagnetic field, of course you have a broadening of each Landau level except the Landau level at zero energy. And what you can show is for twisted biographene and in the Chern limit, you have exactly the same kind of story. So this figure here is that's the velocity at the corner of the Breuer zone, which is just a way to quantify the flatness of the band. This one is the Chern limit, and that's as a function of the angle. The dashed line is when you don't have any disorder. You have here the first magic angle, this is the second one. And you see that if you have disorder, that's the blue curve, you still get a velocity which is very small. So basically, if you do have flat bands at the first magic angle, so the 1 degree I was showing, but the flat band completely disappears for the second one. That's away from the Chern limits, and you get exactly the same kind of story. It's actually very funny because I think in mathematics people are interested in the story of magic angle, and now they have magic angle with complex numbers. But everything that you can say here when it comes to robustness actually works for any type of magic angle, even they are not real.
Question.
Yep.
What does it mean that the lowest Landau level is exactly flat if you have a non-uniform? How do you define the flatness?
You look at the density of states. You see that's basically this plot here. This is the energy, the vertical axis of density of states, and that's the correlation of disorder. And you see that's for what corresponds to the lowest and the Landau level at around zero energy, so n equals 0. As soon as the correlation length is slightly bigger than the distance between two atoms in your graphene, then your density of state is sharply reduced. That's around the zero state. Whereas if you look at the other Landau level, they become flat. Okay, so now coming back to TMDs. So they look like graphene. You have one transition metal and two hydrogen atoms. They differ in the sense that they don't have any inversion symmetry, as opposed to graphene. And there is a very strong spin-orbit coupling and a large effective mass. So if you take a monolayer of the MOT2, the one that people have used experimentally to observe the fractional chain insulators, you see the pretty large gap corresponding to the insulator, and the valence band that we'll talk about is this one around the top valence band array, and basically focusing on what's going on around the K point, like we did for TBG, focusing on the Dirac cone around the K points.
What is the PV in the other? The SV, like this?
I think that's a different type of hybridization. I don't remember the PV space.
Like it doesn't matter. Yeah.
So actually, you can relate twist homobilayer TMDs to TBG. Of course, they don't have the same distance between specific atoms. The twist angle will be the analog of the ideal. The magic angle is different. It's 3.7 degrees, where you have a flatness. But when it's not as stringent as the case of TBG, where you have relatively around this 1.45, people have observed, let's say at least the non-interacting case in a various range of angles, from 3.5 to 4 degrees, and now also around 2.1 degrees. Once again, like for TBG, at least as an angle like the one that we observe the fractional insulators, you're dealing with a large number of atoms. So you need a way to deal with this massive unit cells. Also, a big difference, the TMDs are insulators. They are not semi-metals like in the case of graphene. But actually, it's funny because you can relate the two systems by just doing what you did when you learned the Dirac equation and you want to recover the Schrödinger equation. So you can have a master. If you work in the Carroll limit, it's very funny because you have the two Chern band with the position number. And if you have the proper master, you will just split the two bands. And that's a way to connect to the physics of TMD.
Sorry, this what Vladimir meant? This is what you meant?
I was not thinking about this system in particular, but I could see that. I mean, it seems Carroll symmetric if you.
Yeah, it seems Carroll symmetry.
You still have the Carroll symmetry for because you're still in the Carroll limit. So you can define the Carroll limit for TMDs, like you do for TBG. Yep.
So you're assuming a 2H crystal structure here for these
Yeah.
calculations?
Yes, exactly.
Not 1T, because in the 1T structure, my understanding is that in tungsten ditelluride, it is a semi-metal, right?
Yeah. So yeah, people have used the 2H exactly for
I see.
for this experiment. So once again, I mean, when it comes to continuous model, Alan McDonald is really the king here, and he proposed a model for twisted TMDs. Basically, what you do is you have your two values of your TMD, 1K and 1K prime, so you don't have any universal symmetry. But there is also due to the very strong spin of coupling, you will actually lock the spin degree of freedom and the valley degree of freedom. So the system is way simpler than TBG from that perspective. You can write down an effective model for each valley, K and K prime, which will also be like the spin degree of freedom. At the end of the day, this is the Hamiltonian to describe the continuous model around one value, let's say K. You have a kinetic term, coming from the valence band that you fold, and some Moiré potential within each layer and between the layers. The trick is, of course, the same as MIT. You develop these potentials to the lowest order harmonics, and you have the expression here. And at the end of the day, the only thing that you have left is 4 parameters to define your model. And this is where the ab initio calculations play an important role, because we need some idea of the values of these parameters. It's not, you cannot extract them from the experiment directly. And it's technically challenging because of the large number of atoms, because of the relaxation effect. And this is some result that we have obtained from our collaborators at IOP. You can focus on this one, which includes, this is without relaxation, without static coupling, with static coupling, so you can see how the band structure evolves. And really, you have to pay very careful, pay a lot of attention about, the different acceleration function that you will use, how you take into account the relaxation effect. That's why in the literature you will find historically a very different set of parameters. But I think most recently, at least 3 groups have converged towards roughly the same values. Yeah.
Yes, I guess that's related to my question. Is there a general consensus on what is the best recipe to get this bilayer electronic structure right?
The consensus is like 3 groups. Different groups finding roughly the same range, the same typical parameters for the model. So what the people at OPD really try to do like an extensive study of the different functionals and so on. Try to basically the relaxation effect is really the most time-consuming part of the calculation, as far as I understand. So they use machine learning to actually increase the speed of convergence. But they also try to do like, a direct calculation without this machine learning approach, just to be sure that we are not going in the wrong direction. But they do that by, providing already like the first solution and let the system converge and see if it works. You might wonder why this is important to have an accurate non-interacting model. Well, first you need some idea about the typical energy scales or the bands, because the bands are really dispersive, or the gap is really small. Then the kind of numerical simulation, the interaction regime that you have to perform will be different. Remember that the interaction scale is typically on the order of 20 milliMeV, and if you look at the gap here, you're also the same order of magnitude. But maybe more importantly, just even like the topological characterization of these bands will depend on the parameter that you have. And we find some of the earlier paper, like 2 years ago, where the parameter that they had, the Chern numbers were not the one that you expect now for something at 3.7 degree.
So in assessing the quality of these first principles calculations, is there any direct comparison to experiment? I mean, I'm just wondering if you're just comparing DFT against DFT, like how do you kind of get an absolute sense of how accurate you are?
I mean, that's the usual question. You don't, especially in the system where at the end of the day, it's the combination of interaction and the band structure. So experimentally, it's very hard to. So you want to make a comparison with the experiments?
Well, I just want to have a non-DFT based comparison. So I mean, experiment is the ultimate
Well,
test. There's a way
exactly.
to
So
or something.
the idea is, can you recover all the experimental observation with your model? That's one way to do it. But of course, it's only you could technically change the parameters of your continuous model and still get the same physics. Maybe it's not like you will be able to get a very narrow window on each parameter. So these parameters to be that value between like plus or minus 1 and so on. So that's something very difficult, especially because you have to perform many body calculation, which are highly demanding. So you cannot explore the phase diagram of the parameters.
Right, no, I understand. I guess I know you didn't do the DFT calculations. I'm just trying to get a sense of like how it was realized in the community that you have to be really careful with these parameters. Like, it sounds like this was like a real focal point of first principles effort. Like,
Because, for example, which number will be the second valence band was still a debate a year ago. And at the end of the day, if you can look at the experiments to the observed, depending how you fill the band, what will be for the integer phase, what we will observe, for example, a fin factor phase, which is filling the two valence bands, one in each valley, and then the next one. Okay, so I have 10 minutes. The interaction that you have to consider in the system is the one that is, correspond to the physical setup where you have your twisted system captured in HBN, and you have the top and bottom gates. So it's the screen Coulomb interaction. You will see like a few phase diagram where it's two parameters, the gate distance, but this one is not really that very nice. The gates are far away, actually. One important one is the dielectric constant. And because it's very sometimes hard to know exactly, coming back to your question, what is changing slightly the DFT, for example, might change the dispersion. So what we do is to use 1 over epsilon as a parameter to basically change the ratio between the interaction strength and the kinetic energy. Of course, we cannot do any many-body calculation by including all the bands. So we have to make an approximation. And one of them is to say, well, let's focus only on the top valence band in each valley. Or if we are rich, maybe we can include 2 bands. And also when we talk about filling factor minus 2/3, at least naively, we are talking about filling like 2/3 in terms of whole of, let's say, one value. Maybe as a simple example, look at the case of numerical -1. So like the chain insulator, the analog of the integer multiple effect. And once again, if you want to have an interaction, even if you focus solely on the two top valence then, these two situations have exactly the same energy. Of course, this case is ferromatic, this one is not. And the idea, well, if you look at the experiments, then we know that at filling factor to -1, we do have fermions and we do have a Chern insulator. One way to check what's going on once you have the interaction, because it's at the core, it's a non-interacting phase. In the sense, not sorry, it's an interacting phase, but it's not a many-body problem. You can use Hartree-Fock to get pretty accurate description of what's going on. And that's a typical phase diagram that you compute numerically. You allow yourself to change the twist angle between the two layers. And as I said, you will use 1/epsilon as a proxy to change the ratio between the kinetic energy and the interaction energy. And what you see here in yellow, there is a pretty large region where you do have a Chern insulator, and all the time the system is fully spin polarized and gapped. So when it comes to FCI, we cannot rely on Hartree-Fock anymore. It's a strongly correlated many-body problem. And as usual, the difficulty, like when you deal with quantum spin, is the Hilbert space dimension will increase exponentially with the system size. Because you do have frustration, there is the quantum Monte Carlo doesn't work. It's still exponentially complex to converge. The field is in functional effect use a lot of rational states, but at the end of the day, you have to compare to some numerical simulation. One tool that people have used a lot is exactization. Basically, take a small number of electrons, small system size, factor, and just write down a massive matrix and find the low energy physics of the low energy states. You can also use matrix product states. Anyway, whatever the techniques you have, as usual, it's about, well, know the shortcoming of any of your technique, and in some cases be lucky. In this case, in the sense of having a very short correlation band, so that you can still observe some meaningful physical results, even if you have a very small system size.
So what's the state of the art for exact diagonalization? So how many particles?
It will depend on the filling factor. It's mostly the Hilbert space. If you take like just one band at filling factor 1/3, you're talking about 14 to 15 electrons. And it's on the order of 1 billion for the Hilbert space dimension. Okay, so here are all the experimental results when it comes to FCI that have been reported in the literature. Basically, in transport measurement, people have observed fraction at 2/3 per fifth, and unofficially -4/3. There is either a weak or a normalization at the filling factor of -1/3, and no normalization at all at -4/3. And it's a bit surprising from the FQH point of view because there is a particle hole symmetry in FQH. So usually when you have 1/3, you also have 2/3. Or if you have a spin-full system, if you have 2/3, you should make that 4/3. So that was really a puzzle in the community. And that's a typical angle to observe. So if your model is correct, like the one that you get from TFT and the interaction and numerical simulation, can you reproduce all of them? And the answer is yes. That's basically, I think some of these diagrams are not yet published. You have to be careful in the sense you have not only to get pretty good DFT parameters, but you also have to include band mixing. Band mixing is very important here. It will basically, this is the only way to explain why you don't have any magnetization at -4/3. At 1/3, you do have a charge density wave, and you have, of course, a very strong state at -2/3. Just to present some of the fractions, you can do a simulation at all the filling factors, and you have also similar signature. And even though we don't have access to many system sizes, we can try to extrapolate the gap of the system. Usually, this is actual experimental data, not for twisted MOT2, but for gallium arsenide. You see the scaling of the gap, not really as a function of the filling factor, but some proxy quantity. And you can try to do the same extrapolation of the gap for different filling factors for MOT2 numerics, and it works actually pretty well. So in the last 3 minutes, let me address maybe what people are looking at these days in this system. And it also goes back to the story of the quantum spinor effect. So as already addressed, quantum spinor effect, this time we have the time reversal symmetry. So time reversal symmetry represents the integer quantum Hall effect. In a very crude way, you can think about it as, two copies, two integer quantum Hall effect with opposite magnetic field. So that's what the spin index. So you have two contemporary modes, but they don't break the time reversal symmetry. And the question is, can we get, if you replace here the integer quantum Hall effect by your favorite fractional quantum Hall state, two copies corresponding to two opposite magnetic field, do you get a fractional version of the quantum spinor effect? This topic is also pretty old and has been studied since the late 2000s. There's actually a review article from a few years ago. And also, maybe something important, this kind of system doesn't have any equivalent in a pure gallium arsenide system. But as you saw, when you have the two values of the twisted MOT2, they are related by time reversal symmetry. So that's why the setup is actually pretty similar to this one. Only, for example, when you have T minus 1 out, minus 1, but in integer case, the interaction will give you the magnetism and will give you integer state. But if you have a filling factor, for example, minus 2, you will get a quantum spinor effect in this twisted PMs. So can we, if you take now fractional states and we start coupling them, can we get an FTI? People have looked at that in time models, and you can basically imagine that you take two states at minus 2 further to the one that you showed you numerically, and so one per valley, and start see if the system is stable if you now have interaction between the two values. And at least in toy models, the interaction between the two values, or if you take a negative model with the two layers, it has a tendency to destroy or to destabilize your FTI phase. And as you already saw for my U equal -1, there is a first indication that you have a tendency to ferromagnetize. So if you want to observe an FTI, you need to have an interaction which do not favor too much the ferromagnetic phase, because otherwise you will never get an FTI. You can, learn a lot from the quantum Hall effect, just replacing the band structure that you have for let's say, for twisted MOT2 by just two lambda level with the field, and look at what people did back in the days. And really, the thing that will, so that's more recent work, data that we have obtained in a lambda level setup. The point here is to say that what kills really the FTI is the shortest range interaction that you can imagine between electrons. If you know a little bit about quantum Hall effect, you can use the potentials, which is just one way to develop the interaction, like you develop into SP and so on with scattering. If you're within one layer, you're not sensitive to the shortest range interaction. But this one is important when you come to the interaction between the two layers of the two states. And that's the one that kills your FTI. So what we are working on the moment is to find some suitable interaction that will basically reduce the effect of this short range interaction to see if you stabilize an FTI. Once again, the experimentalists are moving fast. They have a slightly different setup from the one I've addressed. But like a few weeks ago, they have reported maybe the signature. So the first they reported like the observation of the quantum spin Hall effect. But once again, it's time reversal symmetry plus U1, so that's why they have quantum spinor effect at field factor -2, -4, -6. And they have some potential signature of an FTI, not 2 copies of the Laughlin, but what they claim to be 2 copies of the Moiré state. Still under debate, but clearly things are moving in the right direction. And I think with that, I just want to conclude that for people who have worked a lot on fractional insulators, it's really exciting time to move away from toy models to actual experiments. And as usual, the experiments are way richer than what you have in toy models. There are lots of things to understand about some details, why some phases are there, why some are absent. And really, the elephant in the room about me is the FTIs. Can we get something that has never been realized in a gallium arsenide system, potentially then couple them to superconductors? And coupling to superconductors is not a crazy dream. There is a recent paper by the group of Nicolas in Princeton where he does actually the coupling between TMD and superconductor. Also, I've talked a lot about TMDs, but that's not the only system that people have observed FCI. In September last year, there was signature of FCI in a different setup, which is pentalayer graphene, and actually now they also have signature of quadrilateral graphene on HBN substrate. So the HBN substrate is slightly misaligned, so giving them some Moiré pattern also. And they observe FCI state on the top surface. So there's like lots of, there's another example of a setup where this physics emerge. That's why it's not just a fluke. There are several groups, several experimental devices showing the same physics. Okay, and with that, I'd like to thank you for your attention.